Good morning, everyone. Okay, a new week, and there have been like 2 weeks have already passed, and we have already finished the chapter 40 to 70, and today we will learn like the chapter 18, and like it's also about like the optics, like the light, and last week we talked about the wave optics, like the you can see the like light can transmitted can travel in a wave like a model. And in today's class, and we mainly focus on like ring optics, like the light also like can travel in a ring model. So like let's start today's class. Let me share my screen. Yeah. Like I said, today we will mainly focus on ring optics. Mm, Yeah, the ring optics. Okay, let's start today's class. Okay, like for chapter 18, rain optics, and our goal is to understand and apply the rain model of light. Do you remember the goal for the chapter 17, like wave optics? Yeah, to understand and apply the wave model of light. Yeah, we know like there are three different model for the light, like the rain model, the wave model, and the other one is a photon, like the light have the like the particle and wave at the same time. So yeah, in this week, in this class, we mainly focus on the ring model. Yeah, and in chapter 18, like today's class and tomorrow class, we mainly like understand and apply the wave model of light. Okay. Uh, yeah, this is today's goal, like for the lecture 11. Like firstly, we will understand um, the rain model of light. What is the rain model of light? What's the difference between the rain model and the wave model? Yeah. And next, we will learn the principles of light reflection. Yeah, I think the light reflection is everywhere, like in our normal life, in the real world, and but what is the principle of light fraction, and what's the theory behind that? Yeah, and after that, we will explore the behavior of light during refraction. You can see if you see some the atoms under the water, actually, and you usually the distance is far further than what you see sometimes like always. Yeah, sometimes if you fish like I don't know if you guys like fish before. I think most of you maybe fish before, like mm, if you want to catch a fish like by your hand, sometimes you see like this fish is very near, but the real distance is further than that. So like this is some refraction. So like we will explore the behavior of light during refraction. And finally, we will understand image formation through refraction. Yeah, this is what we will learn in this class, in this lecture. Okay, let's continue. And let's do some previews about the chapter 18. And firstly, let's talk about reflection. Reflection, like light rays can bounce or reflect off a surface, like rains from the ghost head. You can see rains from the ghost head reflect from the water, forming an upside down image. You can see here. Here is a real dark. Here is a like a like upside down image. Yeah, this like a phenomenal. Actually, this image because of the reflection. Yeah, You will learn how the law of reflection can be used to understand image formation by mirrors. You can also like every day, I think you will like look yourself in the mirror. But what's the theory behind that? Yeah, today we will learn that. And but remember, after we learn that, you only know like why like you can look yourself in the mirror, but you cannot like make yourself like more handsome. Yeah, after we learn that, just kidding. Okay. Then we will like learn something about refraction. Yeah, yeah. I think this image is interesting. Is an interesting one. Like it's like a funny one. Like the two images of the frog you can see are due to refraction. The bending of light rays as they travel from one material into another. Yeah, here is air, here is water, and the light from the water like from the air to the water, it will have the refraction like a phenomenon. So like sometimes the image seems weird to you. Yeah, you will learn Snell's law for refraction and how images can be formed by refraction. Yeah, and also we will learn some like lenses and mirrors, like rays in refracting at the surface of this lens from a magnified image of the person behind it. Yeah, like you can see here, if we see something from um, from some lenses or mirrors, like rays reflecting at the surface of this lens, form a magnified image of the person behind it. You will learn how to locate sorry, you learn how to locate and characterize the images formed by lenses and mirrors. Yeah, we will learn this in tomorrow's class. And let's try to looking back something like the wave model of light. Yeah, in chapter 17, you learn that the light spread out. Yeah, you can see the light spread out as it passed through a narrow slit. Yeah, and but travels straight. Yeah, here you can see it travels straight forward through a wide open openings. Yeah, if this opening are very small, actually it the unit should be like a millimeter, micrometer like that. Micro and there will have some like wave model phenomenon such as like a diffraction, yeah, interference thing. Yeah, we have learned this in chapter 17. But if this narrow, this like a slit is this opening is very big, it will travel straight forward through the wide opens. Yeah, this is what we learned in chapter 17. And in this chapter, we will study the behavior of light in the rain model. Yeah, applicable when light interacts with objects of everyday size, such as mirrors or lenses. Yeah, this is what we will learn in chapter 18. Yeah, okay. Let's try to stop to think these questions. The dark screen has a 2 millimeter diameter hole. The bulb is the only source of light. What do you see on the viewing screen? Yeah, actually, you can see here is a circle. Am I right? Yeah, I think you will easily think about the circular aperture. Am I right? Like we learned in chapter 17. Maybe you will think the option D is the right answer. But you need to notice the two things. The first one is the hole, like this hole is 2 millimeter diameter. I talked about this. If the slit, yeah, the size of slit should be very very small for the like wave model. It should be like the unit should be like a micrometer. but here it is millimeter. It's not small enough. And first and the second, like when we talk about the diffraction, the interference phenomenon in the chapter 17, we mainly focus on the light is a beam light, is a laser light, or some a visual spectral visual light like that, the red light, green light like that, and the wavelength is very small. Yeah, it is the nanometer, the unit is nanometer. But here, the light source is a bulb. So, which means you cannot use the what we learned in chapter 17. We will learn something in this chapter, and you will know the right answer. Actually, the right answer is B. You can see it will opposite, and in the view thing it will have the you can in this view thing you can see the original light source, but in a opposite in a flip display. Yeah, so the right answer should be B, and we will know why this is the right answer after we learn everything in this chapter. Yeah. Okay, let's continue. Okay. Sorry, I think I just put two things. Okay, I put oh, I will delete those later. Okay. Firstly, let's talk about the rain model of light. Yeah, the rain model of light which ignore the rain model of light which ignores diffraction. Yeah, we talk about diffraction. Yeah, this diffraction, which means if the light goes through a very small slit, or multiple slit, or diffraction grating, and there are some a situation. It's called diffraction. Yeah, but for the rain model of light, which ignores the diffraction, is valid as long as any apertures through which the light passes are larger than about 1 millimeter. Yeah, which means if there is a opening, the size is larger than about 1 millimeter, and you can ignore the diffraction, and the light will have the wave rain model. It will not have the wave model. Does it make sense to you? Yeah, and a light rain is a line in the direction along which energy of light is flowing. For example, this here, this is direction of light travel, and this is light rains. And the light rain is a line in the direction along which energy of light is flowing. A laser beam is a good approximation for light rains. Yeah, you can see if you open a laser beam and give you a straight line like that. For example, this one. Yeah, I forgot to. Yeah, for example, for about this lens. Yeah, it's just some straight lines like that. Does that make sense to you? Okay. Let's talk. Yeah, light rains are straight lines. Light rains are straight lines. Light travels through a vacuum or a transparent materials in straight lines called light rains. Yeah, and the speed of light in a material is V equals C divided N. The V is just the speed of light in a material, and the C is what? Yeah, the light speed in vacuum, and the N is what? It is the index of refraction. We talk about this in chapter 17, if you recall. the video and the slides, you will know that. And wherein is like intentional refraction of the material. And you can see here, this is just like a light rains, and this is two light rains. Yeah, the light rains can cross. The light rains do not interact with each other. Two rains can cross without either being affected in any way. It's just not like a model wave. It will have the interference phenomenon. It will generate like it will have the like the diffraction situation. Yeah, the light rays actually they can cross with each other and without either being affected in any way. You can see here, there are some like you can see this street, this light rays can be crossed. Yeah, does it make sense to you? Okay. Okay. Um, the rain model of light, like let's continue to talk about the rain model of light. A light rain goes on forever unless it interacts with matter. Yeah. Actually, like a light rain can goes on forever. Like, but usually it will like it will like meet obstacles or some like surface. Yeah, unless it interacts with matter. A light rain continues forever unless it has an interaction with matter that causes rain to change direction or to be observed and observed. Light interacts with matter in four different ways. Yeah, actually, light interacts with matter in four different ways. Different ways. Yeah, one is like a reflection. Like if the rain, if the light rains meet the surface, it will the light will be reflected. The other like situation is refraction, and you can see if it meet this surface, and it will have the refraction situation. And sometimes like if the rains, light rains meet some like particles, some small dust, or some like smoke things, it will have a scattering like a situation phenomenon. And the next one, if like this, there is a net, and there, if it will be observed like by something, yeah, like this. There are four different ways, and at an interface between two material, light can be like reflected, refracted, or both. With a material, light can be either scattered or observed. Yeah, this is four different ways. And those interactions are discussed later in this chapter. Okay. And an object is a source of light rays. Yeah, actually, an object is a source of light rays. Rays originate from every point on the object, and each point sends rays in all directions. Objects may be luminous. They created light rays, or they may be reflective objects that reflect only rains that originate elsewhere. Yeah. For example, there is a tree. Yeah. Actually, the tree, like it is itself, like it is not a self-luminous thing. Am I right? There is no self, but this tree can reflect the sunlight. I'm right. So actually, yeah, we can like see the light from this object like in different direction. Yeah, this is what this means. And yeah, this object is a source of light rays. Yeah, actually, our human body, you can see if other people can see us, and because like our body can reflect different the light in different directions. Yeah, does it make sense to you? Yeah, like actually we are like reflective objects. Yeah, we can reflect the rains that originate elsewhere, such as sunlight, such as the light from the bulb. Yeah. Okay, like the eye sees by focusing a bundle of rays. You can see this is eye. This is an object. The eye sees an object when diverging bundles of rays from each point on the object enter the pupil and are focused to an image on the retina. Image is discussed later in the chapter. Yeah, this is how our eye see an object. Yeah, actually, our eyes here uh, there is a thing in our eyes, and those things can make the light into our object to cross in one point. Yeah, and then our eyes can see this object. Yeah, like does it make sense to you? Yeah, our eyes can diverging bundles of rays from each point on the object into the, yeah, this is just the end and the start and the end. Actually, for this point, they have the same thing. Yeah, they have the same thing. And yeah, to this point, yeah, it's just only 2 point here, but you can draw different point. Yeah, and each point on the enter the pupil and focus to the image on the retina here, the retina, and then we can see the image. Does it make sense to you? See the object. Okay, actually, based on the objects we can see, like I said here, there, uh, yeah, an object is a source of light rays. Yeah, and this object can be self-luminous, and also it can be reflective objects. Based on this, there are two different objects, like a source of light rays. Yeah, source of light rays. And the first one is self-luminous objects or sources directly create light rays. Self-luminous objects include light bulbs and the sun. Yeah, this is obvious. Yeah, those two things can directly create light rays. And the other one is reflective objects, those objects reflecting like rains originating from self-luminous object. These objects include a piece of paper or a tree. You can see a tree, our human body, like a piece of paper. If you see the paper, actually you can see the paper cannot directly create light rays. And it's just the sunlight or some like bulb light reflected the light to our eyes. Yeah, does it make sense? Also, like the moon. Yeah, like the moon cannot directly create light rays. Yeah, so there are two different kinds of objects for the source of light rays. Firstly, let's talk about what is a rain source. Yeah, since a light rain is an idealization, there are no true rain source. You can see we talk about a light rain. It's just an idealization, ideal like idea. Like a light rain is an idealization. There is no true rain source. Still, the thin beam of a laser is often a good explanation of a single rain. Yeah, you can see if you use a laser, and there will be a, light rain. Yeah, we can consider it as a single rain, but it is not. Yeah, it is just a good approximation. Okay. After we talk about a rain source, let's talk about a point source. A point source is also an idealized source of light. It is infinitely small and emits light rays in every direction. Yeah, like a point source, which means this is a very small. The source is very small and emits light rays in every directions. Yeah, this is just a direction, but you should see every direction. The tiny filaments of these bombs approximate point sources. Yeah, like this tiny filaments of these bombs, we can consider it as a point as some point sources, but it's not. Yeah, it's just like a approximation. Yeah, it's like the rain source, and this is a point source. Yeah. You can just remember like a laser is just we can consider it a rain source, and like those tiny filaments of these bulbs we can consider it as a point source because it's very small. Yeah, and it emits light rays in every direction, and uh, and extended source, like this is the most common light source. The entire surface of an extended source is luminous, so that every point of an extended source acts as a point source. Light bulbs, flames, and the sun are extended source. Yeah, like those kind of source we see like often more often in the real world, such as like sun, light bulbs, flames, like that. Yeah, the entire surface of an extended source is luminous. Yeah, so that every point of an extended source acts as a like a point source. Like here, there is it's just similar. Like here is a point, here is a point, blah 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 blah. Yeah, over all over this extended source. Yeah, this is like a three different self-luminous source. Yeah. Okay. Uh, Also, like there is another source. We call it a parallel rain source. Like certain sources, such as flashlights and moving projectors, produce a bundle of parallel rays. Rays from a very distant object, such as a star, are very nearly parallel. Yeah, you can see. Uh, because this star here, there is a star. It emits some like some like rays because this distance is very far, very far. When if you like just see this part of rain lens, it just you can consider it is parallel. Yeah, so we consider it is a parallel rain source, and this is some like a torch, like yeah, we use it can emit some like a parallel rain source. Yeah. Yeah, those like those four like different self-luminous objects which can uh, emit like some lights like deep, yeah. Okay, and then let's talk about the rain diagrams. A rain diagram is a diagram that shows a few light rains in order to simplify the situation. Yeah, in reality, rains originate from every point on an object and travel in all directions. Yeah, here, these are just like here. Yeah, these are just a few of infinitely many rains leaving the objects. Yeah, here and here. But this is a rain diagram. But actually, in the real situation, yes, it's just now those two. Yeah. Uh, yeah, of course, I'm right. I think you can understand that because you can see here for a tree, it's not only those two like two location like it makes some rains. Yeah, also here, 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 here. But usually when we want to like simplify the process to show some problem, so we just use those ring diagram. Yeah, like yeah, in reality, like rings originate from every point, but in a ring diagram, we just use those 2 points to show some to like explain some situation. Yeah, that makes sense to you. Okay, let's talk about how can we see objects like. In order for our eye to see an object, rays from that object must enter the eye. Yeah. For example, here is a laser beam. Yeah, here is a laser beam. If our eye is here or here, yeah, if you stand here and stand here, actually you cannot see the like laser ray. That makes sense to you. Yeah, you can try that. Yeah, you can now see the laser beam traveling across the room because no light from the laser enters the eye. Yeah, if you just your eye is here, yeah, you can see this ring, but here, you cannot see this ring because no light from the laser enters the eye. The beam is invisible to you. This is the case for ring or a parallel ring source. Yeah. Yeah, but sometimes maybe some students will ask a question. If I use a laser beam and I can see a dot on the ground, and I'm right on the floor like that. Yeah, that's because when you use a light beam and this light ring, this yeah here, for example here, uh when the light ring, for example here is a wall, like meets the wall and then it reflect some lights. And if your eyes is here and this reflect light into enter into your eye, you can see the like see that dot, which it doesn't mean you can see this light. You only can see the flashlight. Yeah, that makes sense to you. Yeah. Okay. Yeah, a point source and an extended source emits rays in every direction. We talk about that. And some of the rays will enter the eye, no matter where it is located. Yeah, because you can see we talk about it like a point source. A point source and an extended source because they emit rays in every direction. Yeah, actually every direction. So like there must be some rays, yeah, will enter into our eye no matter where it is located. Yeah. For a ball, yeah, for small like a small we will talk about this for small yeah here. Yeah, for small tiny like filaments of these bombs. Yeah, even it is very small, but it emits different like the rays in different directions. So our eyes can see that because yeah, does it make sense to you? Yeah. Uh, Thus, a point source or an extended source is visible to all observers. Yeah, it must be that. Yeah, because we can see the light no matter where we are. Yeah, because it emits the light in every direction. And let's talk about two different phenomena. One is diffuse reflection. Yeah, it is the process of reflecting incident light in all direction. Yeah, and there is another one we call it scattering. It is a process in which single rays are broken into many weaker rays that lives in all direction. But some students maybe have the question, what's the difference between diffuse like a reflection and scattering? Yeah, there are some like difference. And if you focus if we compare the focus on the diffuse reflection, usually it happens in a on a rough surfaces. Yeah, for example, like a rain light, like they meet a wall, meet some clothes, meet some some rough surfaces, and then it will have the diffuse reflection. And if a rain light, like the inside a medium such as a gas, a liquid, a smoke thing, and then it will have the scattering. Yeah, that makes sense to you. And let's talk about from the light behavior what's difference. The diffuse reflection reflected in multiple directions. Yeah, it will like a it will like reflect incident light in all directions. But for scattering, it observed and re-emitted in random directions. Yeah, like if the rain, the incident, like a light, they enter into some like medium, like a smoke, gas, liquid, and the light will be observed and emitted in random directions. Yeah, you cannot like calculate like predicted the directions, but for diffuse reflection, actually you can calculate the like reflected direction. Yeah, and let's talk about it from a base reflection law. Yeah, it is. Yeah, because it will reflect those like rain incident rain will be reflected and obeys reflection law. But for the scattering, it will not. Yeah, because you can see it will be emitted in random direction. We don't know which direction it will be like emitted. So we can now use the reflection laws to resolve these problems. Yeah. So there are some examples, like for example, like in in like the incident light, like the rain light, like meets papers, walls, clothes, and they will have this diffusion reflection situation. But if the light rain like enter into like blue sky, fog, smoke, yeah, it will have scattering situation. Does it make sense to you? Okay. That's how when reading a book, every point on the surface of the page is struck by a ray from the lab. Yeah, that's a reason why you can like when you're reading a book, you can see every word on the book. And then because of diffuse reflection, these rays scatter in every direction, some of which enter your eye. Here, this scatter is just a like verb, like a verb word. It's not. It's different with this, like the scattering we talk about that. Yeah, it's just like this rays reflected in every direction. Yeah, yeah. Here is like a rain diagram. Here is a rain diagram. And incident rain breaks into many weaker rains that scatter, yeah, in every direction. And some scattered rains enter our eyes, so the point is visible. Other points on the page are visible in the same way. Yeah. And lasers are visible when small particles such as dust, smoke, or water droplets scatter the rays from the laser in every direction, like here. And some of the rays are scattered in the direction of your eye, making the particles in the path of the laser visible. Yeah, this is just some like an example of scattering. Yeah, this is the example of diffuse reflection, and this is an example of scattering. Yeah, does it make sense to you? Yeah, when the laser beam enter into the dusk, here is the dusk smoke. Here are some dust, smoke, and then the instant rain will meet the smoke particles, and it will like scatter in every direction randomly. And but some these rays reach the eye, making the path of the laser beam visible. Yeah, this is an example of scattering. If you look up at the sky, you see light redirected to your eye by scattering from air molecules in the atmosphere. The light rays that reach your eyes are mostly from the short waves end of the spectrum, and that is why the sky appears blue. You can see here, this is a long wavelength. It is a long wavelength. It will close to red. This is a short wavelength close to uh, blue and violet. Yeah, so like if you look up at the sky and you see the light directed to your eyes, to your eye by scattering from air molecules in the atmosphere. Yeah, and the short waves end of the spectrum, this part. Yeah, that reach your eyes. Yeah, this is why the sky appears blue. Actually, we talk about this in NASA class. Yeah, we talk about like because of the thin films, like a phenomenon, the air molecules in the atmosphere scatter light. Yeah, allowing like a long wavelengths to pass through, and the short wavelengths to scatter, making the sky blue. Yeah, we talk about this in NASA class. It's the same thing. Yeah, it's just like use the scattering to situation to like explain why the sky appears blue. Okay, and let's talk about the shadows. Yeah, an opaque object can intercept rays from a point source, leaving a dark area or shadow behind it. You can see here there is an opaque object. It can intercept rays. Yeah, this is the rays from a point source, leaving a dark area. Here there is a shadow behind it. With light from a point source, the shadow is completely dark, and the edges of the shadow are sharp. You can see the edges of the shadow are sharp, and the shadow is completely dark. And an extended source is a large number of point sources. Yeah, yeah. Here is the point sources. Here. Yeah, it's a large number of point sources, each of which casts a shadow. Actually, each of which casts a shadow. With light from an extended source, the pattern of the shadow and the light from each point overlap. Yeah, you can see the shadow and light from it will overlap, and thus the shadow region is no longer sharp. Here, the shadow region is there is no longer sharp. Yeah, and depending on the size of the source, there is often a true shadow that no light reaches, surrounded by a fuzzy region of increasing brightness. You can see here. If you view a bomb as seen from 3 points on a screen, yeah, the whole bomb is visible from point A. Here is the point A. Point A is fully illuminated, and at B, the the disk partially obscures the bomb. Point B is in partial shadow, and at C, the disk completely blocks the bomb. Point C is dark. You can see this point is dark, and this is visible from like the whole bomb is visible from here is partially. Yeah, like depending on size of the source, there is often a true shadow that no light reaches, surrounded by a fuzzy region of increasing brightness. Yeah, and okay, let's talk about this question. Actually, we talk about this question in the beginning of the class. The dark screen has a small hole. Yeah, here is a dark screen. Yeah, has a small hole like around like 2 millimeter in diameter. And the light bulb is the only source of light. What do you see on the view screen? Actually, because of you can see here the light will, because this is the hole is now that tiny, and the light is now like the small wavelength light is just uh, the big source, the extended source, like a light source, and there are so many point source here. So in the view screen, we can see uh, the flip like a bomb. Yeah, we should choose B. We have already talked about this, and yeah, the answer is that one because the light you can see here it will yeah directly to the hole from to here, and this point will direct to this hole and reach here, and then it will give you a flip image. Does it make sense to you? Okay, and let's talk about this question. Two-point sources of light illuminate uh, illuminate a narrow vertical aperture in a dark screen. What do you see on the viewing screen? Yeah, actually, you can see here. This is a point source. This is a point source. This point source, maybe they will have some like a ring light, ring light, and it will give you yeah. Actually, it will give you a bar. Yeah, like a similar bar here. And then this light also it will ring light. It will have a ring light. Yeah, it will different. This will give you the same bar. Yeah, so the answer should be this one. That makes sense to you? Yeah, if you draw that. Yeah, yeah, it's the right answer will be C. And let me draw it. Yeah, and for example, we just give you one. Yeah, from here to here and from here to here. Yeah, yeah, we can get a one bar. Yeah, and then from this one, yeah, we get this one, from this one, get this one. Yeah, we have the other one. Yeah, so we can get Z. That makes sense to you? Okay, let's talk about one exam problem. If the aperture is very small, here is the aperture, very small aperture. How far apart on the screen built into the left side of the box are the images of the point like red and green light sources? Yeah, here is two sources. This is a red one. This is a green one, and the distance between the red one and the green one is 5 centimeter. And here is the distance, the light source to aperture, and this is distance from the aperture to this is like a wall or like a screen like that. Yeah. Yeah. So the question is ask us like how far apart on the screen. Here is the screen built into the left side on the box are the image of the point like red and green light sources. Actually, yeah, for this problem, yeah, actually like there is a like a law. Yeah, this one, if this point goes into this one, and it will give a like a similar like this, and this one will give a yeah similar like this, and this yeah actually it will have a two. It will form a two triangle. Yeah, this is triangle one. This is triangle two. This triangle will have like a will have some will obey some rules, and this one this distance uh compare with this distance, it's equal this one. compare with this one. This one, we for example, we set it as L, and this is like a 5 divided L, like the ratio is the same thing, like a 10. This divide this one. Yeah, this is I think you have already learned this in high school or the other like former chapters. Yeah, they have this like a relationship. If you draw this and you can get this equation. 5 divided L equal 10 divided 50, which means L equal what? L equal 5 multiple, that makes sense to you, and this is 1.5, which means like this distance, how far? Yeah, equal 7.5 centimeter. That makes sense to you? Yeah, because you have this relationship. Yeah. Okay. Let's talk about the other like section. Yeah, reflection. And we have already talked about the light, the rain model for the light, and the different light sources, and the what how can we how can our eyes see an object, and yeah, and in this section we will talk about reflection. And specular reflection is a reflection from a smooth shining surface such as a mirror or a piece of polished metal. You can see here is a reflective surface. It's very smooth, and it has a very smooth and shining surface such as mirror or a piece of polished metal. And a dimensional perspective shows that the incident and reflected rays are both in a plane that is normal to the surface. Yeah, which means here, this is the incident rays, and this is like a reflected rays. Yeah, this is reflected rays. Let me make it clear. Yeah, this is incident, like rays, and this is the reflected rays, like corresponding to this one. And those two, like they are in both, they are in this plane here. They are all in this plane. And this plane is normal to the surface, to this surface, which means it is here is 19 degree. It's just yeah, like this plane also. Yeah, this plane, yeah, this is normal to the surface, which means there is like a 90 degree angle, and which means this plane is perpendicular to this surface. Yeah, and it is customary to represent reflection with a simpler view. Yeah, we can use this diagram to simplify like how the light do the reflection. The incident, here is the incident ray, and the reflected ray are in the plano page. Yeah, here the and the reflective surface extended into and out of the page. Yeah, you can imagine that. Yeah, this is it is in the fridge like a page, and this one is just in out of the page. And a single light ray represents the entire bundle of parallel rays. This is oversimplified, but it keeps the figure and the analysis clear. Yeah, this is just a one ray. one light ring, one incident ring, and one reflected ring. But in the reality, it is so many like a parallel rings. Yeah, we just want to use this simple one to describe the law, the inflected law. Okay, let's continue. And the angle of the incidence, yeah, this is the angle. This is the angle of incidence, and it is the angle between the incident ring and the normal. This is the normal, and the line perpendicular to the surface. There is a line to the perpendicular to the surface. We call this normal line, and yeah, this angle we call it angle of incidence, and the angle of reflection, theta r. Yeah, it is the angle between the reflected ring and the normal to the surface. Yeah, there is a law of reflection states. Yeah, the incident ring and the reflected ring are both in the same plane, which is perpendicular to the surface. Yeah, we have to talk about it. The angle of reflection equals the angle of incidence, which means the theta r equals theta I. There is a note like optics calculations always use the angle measured from the normal, not the angle between the ring and the surface. And just pay attention. Better pay attention. Yeah, usually we calculate. We just use this angle and this angle. Not this angle. Just Now this one. Now this one. Yeah. Okay. Let's talk about one example, like a light reflecting from a mirror. Yeah, a full-length mirror on a closet door is 2 meter tall. Yeah, here is a mirror. Sorry, use a pen. Here is a mirror. It is 2 meter tall. The bottom touches the floor. Yeah, here is the floor. Berry light bulb hangs 1 meter from the closet door. Yeah, here is a closet door, and here there is a bulb, and this distance 1 meter from the closet door, and 0.5 meter above the top of the mirror, which means this from here to here. Sorry. From here to here, there is a 0.5 meter. And how long is the streak of the reflected light across the door? Yeah, they just ask you how long is the streak of the reflected light across the door, across the floor. Yeah, here how. Yeah, how long is reflect? Yeah, they just ask you how long of this distance if the light there is the top and reflected to here, and this is this is just the bottom light. Yeah, and how long is this distance? Okay, let's try to resolve this problem. We still treat the light bulb as a point source, then trace rays of the light from the bulb. Yeah, firstly, let's treat it as a point source, then trace rays of light from the bulb and use the law of refraction to see where they strike the floor. The range of the rays that strike the floor will be the length of the streak. Yeah, and the figure is a visual overview of the light rays. We need to consider only only there are 2 rays that strike the action of the mirror. Actually, you don't need to consider this one. Yeah, this one, because it's just in the middle. You want to calculate the longest. Doesn't make sense because how long is across the door? Yeah, you just need to consider the longest. and all other reflected rays will fall between those two. And the rain that strikes the bottom of the mirror reflected from it and hits the floor just where the mirror meets the floor. Yeah, here. So here. Yeah. The bottom floor just reflect from it hits the where for the top rain, this rain. And the figure has used the Lorner reflection to set the angle of reflection equal to the angle of incidence, which means here, this one, theta, we call it theta, and it should be equal this one, theta. That makes sense to you? So, yeah, we can call both theta. By simple geometry, the other angles shows are also equal to theta. Yeah, we have already talked about the theta r equals theta I. Yeah, theta I equals theta r. That makes sense to you? Okay. And let's solve. So from the small like a triangle at the upper right, yeah, here. Let's make it clear. Yeah, you can see here there is a triangle. Here, yeah, we know this distance is 1 and this distance is 0.5, and we can calculate theta based on those two. Yeah, why? We know. Oh, sorry. We know this is theta, am I right? Yeah, we know this is theta. Why is this is also theta? Yeah, we know this is theta, am I right? So because this line and this line is parallel, so which means this angle equals this angle. Yeah, this is the basic geometrical thing, am I right? And this one equals this one. So which means this distance we know it is 1. This distance we know it is 0.5, which means we can easily calculate this angle. Am I right? So this angle is what? Is tangent. Yeah, because tangent state equal 0.5 divided 1. Am I right? So theta equal tangent. Yeah. And it is around like 26.6. Yeah. But we also have tangent theta equal this one. Why? Let's talk about why. Yeah, because here, let me try to get clear. Yeah, because this one is also theta, right? Yeah, this one and this one is parallel, right? So which means this angle equals this angle, right? Yeah, so which means like tangent theta also equal to divide L, right? So for now we know tangent theta, right? And we just want to calculate L. Does that make sense to you? So L equal what? L equal 2 divided tangent L. Yeah, real tangent L equal this one. So because we know like the tangent actually the tangent theta equal 0.5 divided 1 is 0.5, right? So which means the L equal 4 meter. Yeah, that makes sense to you? Yeah, the visual overview was drawing more or less to scale, and the length of the streak on the floor seems about twice as long as the mirror, so we can have confidence in the results of our calculation. You can see from here. Yeah, you can see it almost twice those 2 meter, am I right? So we should be confident in the result of our calculation. Okay, let's talk about the other one. Yeah, looking at the image of a pencil in a mirror, what do you see in the mirror if the top half of the mirror is covered? Yeah, for example, here is the middle node. If the top half of the mirror is covered with a piece of dark paper, which means this one is also become very, very dark. So, like what do you see in the mirror if the top half of the mirror is covered with a piece of dark paper? Which one? Guess. Yeah, actually, you can do this experiment in your mirror, in your own mirror. You can see even this part of mirror is covered, and the light can also enter into your eye. Actually, you can see if the light is just like this, and then the light will and this light is you can see the pencil is just like this. Yeah, it's just the reflection. Yeah, you can see. Yeah, the light even this part is covered, and yeah, the light you you can see. Yeah, from here you can see this pencil. Yeah, so which means you can see the full image of the pencil. Does it make sense to you? Okay, let's talk about the diffuse reflection. On the microscopic scale, yeah, the surface of a diffuse reflector, yeah, paper or cloth, you can see if this is a paper or flex. This is magnified view of surface using some microscopic scale. And the law of reflection holds, but the irregular, irregular, sorry, the irregularities of the surface cause the reflected rays to leave in all directions. Yeah, you can see each ray obeys a law of reflection at this point, at the specific point. But the irregular surface causes the reflected rays to leave in many random directions. Yeah, sometimes you will see the reflection rays is now parallel. Even the incident lens is parallel. That's because the surface is not like a mirror or some polished metal thing. Yeah, it is very rough. So this irregular surface cause the reflected rays to live in many random directions. Does it make sense to you? Okay. A plane mirror is a flat mirror, like a rays from point B. Yeah, will reflect according to the law of reflection. I think this is normal, am I right? Yeah, because this is a mirror, the mirror is a flat mirror, and rays from P, yeah, reflect from the mirror. Each rays obeys law of reflection. You can see this one. Yeah, if you draw a norm, you can see this one. These two angle will be equally. If you draw a norm for this one, this one, and this one is equal. And if you draw a norm from this one, this is equal. If you draw, yeah, this and this is equal. Yeah, that makes sense to you. Okay, the dashed lines indicate that the rays appear to have come from the point P dot. All reflected rays appear to come from point P dot. Yeah. Yeah, these reflected rays appear to have come from point P dot. If you uh, uh, see there is an eye, yeah, you can see this P dot it's just exactly this object P. This dashed lines indicate that the rays appear to have come from P dot. All reflected rays appear to come from the P dot, which means, yeah, For them here, you just like connect all the sorry. You connect all the reflected lens here and here. You will see this is a P dot. Yeah, like all, which means all reflected rays can be connected to and connect to one point. This point we call it the P dot. Yeah. Okay, and point P dot from which the reflected rays diverge is called the virtual image of P. Yeah, we call this P dot is virtual image. The image is virtual because no rays actually leave point P dot. Actually, this P dot, like there is no rays actually leave P dot. However, the light waves act exactly as they were. Yeah, that makes sense to you. The image distance S dot is equal to the object distance S dot equal S for the plane mirror, which means this distance equal this distance. Yeah, that makes sense to you. Okay. The eye captures and focuses divergent bundles of rays from each point of the image of an extended object. Rays from each point on the object spread out in all directions and strike every point on the mirror. Only a very few of these rays enter your eye, but the other rays are very real and might be seen by other observers. Rays from point P and Q enter your eye after reflecting from different areas of the mirror. This is why you can now always see the full image in a very small mirror. Yeah, you can see this is an object. This is a P dot for P, this Q dot for Q, and you can see you can see the whole tree if the mirror like this long. But if the mirror like just this long, you may now you cannot see the object. If it's just like this tall, yeah, maybe you just can see half. Does it make sense to you? Yeah. Let's talk about some quick check questions. An object is placed in front of a mirror. The observer is positioned as shown. Yeah, here is the observer. Here is the object. Which of the points showing best indicates where the observer would perceive the image to be located? Yeah, I think this one is easy. Here is a mirror, and actually from the reflection law, we know there will be a mirror object image here. Yeah, because this is a same distance as dot, am I right? So you for the like observer, you can see there will be a. Does it make sense to you? Okay, the answer should be C, am I right? Okay. And let's talk about one example, like how high is the mirror? If your height is h, yeah, your height is h, and what is the shortest mirror on the wall in which you can see your full image? Yeah, let's talk about this example. Like we will use the rain model of light. If the mirror is tall enough, there will be a path for rays from all parts of your body to reach your eyes. And you will be able to see your full image. Yeah, that makes sense to you. Yeah, if there will be if the mirror is tall enough, there will be a path for rays from all parts of your body to reach your eyes, and you will be able to see your full image. As a figure, this figure is a visual overview of the light rays. And yeah, here is the light rays, here is the light rays. Yeah, and we need to consider only the two rays that leave the top of your head and your feet and reflect into your eye. This is just simplify this question. Yeah, we assume there is only two light rays. This is the one, and this is the other one. One is from the feet, the other is from the head. And that the distance from your eyes to the top of your hand, yeah, here. For example, here is your eye, and here is your head. The distance here it is L1, and the distance to your feet is L2. Your height is like obvious, like L1 plus L2. A light ray from the top of your head that reflects from the mirror at theta r. Yeah, which means a light ray from the top of your head. This one. That reflects from the mirror at this one here. This is theta, right? Theta r. This is theta r, and theta r. These two angles should be the same, and each enters into your eyes must, by congruent triangles, strike the mirror a distance half L2. You can see here it should be half L2, half L1 above your eyes. Similarly, a ray from your foot to your eye strikes the mirror noble. Yeah, you can see here, and this angle and this angle will be the same thing. And the distance, and this one to this, from here to here, from here to here should be half L2. Am I right? Yeah. At least, yeah, to ensure that the light can enter into your eye. The distance between those 2 points on the mirrors is half L1 plus half L2 equal half H. A ray from anywhere else on your body will reach your eye if it strikes the mirror between these 2 points. Yeah, for example, here, yeah, this one will enter here, and it will enter into your eyes. Yeah, and does it make sense to you? And thus the shortest mirror in which you can see your full reflection is half H. Yeah, because those two plus together is what? 2L1 plus L2, am right? L1 plus L2 equal what? H, am right? So it is half H. Yeah, so the shortest mirror in which you can see your full reflection is half H. At no point in our derivation did we use the distance from you to the mirror. This makes sense. Getting closer to the mirror doesn't allow you to see more of your image. It just gets you closer to the image. If you doubt this result, try it. Okay, I want to talk about more why this is half L1 and here is half L2. Okay, let's see. Sorry. Let me make it bigger to let you guys see it clear. Yeah, here. You can see here, like we needed to, this is an incident, like a rain. This is a reflected rain. And here, this is the norm, am I right? I need to make it straight. Yeah. This is the incident, this is the reflect, and this is yeah, this is the very straight, which means these two angle is the same angle, and this one, and there is a 90-degree angle, and this norm line is perpendicular to this surface, and which means here, if there is a, and if you connect it to here, and this one is just a half, and this is just this distance, am I right? And this distance should half this one, am I right? Because otherwise this one will now perpendicular this one, am I right? So which means this distance must half L1, because this is L1, am I right? This should half L1. That makes sense to you? Yeah. And this one, the similar thing, because you can see here, you just find the norm line, and this angle equal this angle, am I right? Theta I, theta R, and like here is 90-degree, am I right? So which means if you connect this to this, and it should yeah, and which means this part, yeah, should same this, and should be same with this one, am I right? Because this angle, this two angle is the same thing, same angle. So which means this distance should be half L2, am I right? Because the total is L2. That makes sense to you. So that's the reason why here is half L1 and here is half L2. Okay, this is just I want to make it more clear. Okay, and then the total is the like a mirror, the shortest mirror should be half H. Yeah. Okay, let's talk about refraction. Yeah, what is refraction? And two things happen when a light ray crosses the boundary between the air and the glass. Yeah, part of the light reflects from the boundary, obeying the law of reflection. This is how you see here. This is a reflected ray. This is how you see the reflection from pools in water or short front windows, even though water and glass are transparent. Yeah, and part of the light continues into the second medium. Yeah, it is transmitted rather than reflected, but transmitted ray changes direction as it crosses the boundary. The transmission of light from one medium to another, but with a change in direction, is called refraction. Actually, yeah, like this is like a like the refraction situation, like a phenomenon. Yeah, actually refraction like not just happen between the air and the glass, the air to the water, the air to the glass, or some other materials, and yeah, two different materials, like yeah, part of the light reflected and a part of the light will refract, will like have the refraction situation. And what is reflection? It's just like the transmission of light from one medium to another, but with a change in direction. It's called reflection. You can see here, and it will, it should if it is just like a if it will not change the direction, it will go into this one, right? But it change the direction, it will go this one. If it is not go change the direction, it will go this one, but it change, so it goes this one. Does that make sense too? There happens two time refraction. Yeah, from the air to the glass, from the glass to air. Yeah, this is a rain refracted at air glass boundary. This is a rain refracted at glass air boundary. Yeah, that makes sense to you? Okay. This figure shows, this figure shows the refraction of light rays from a parallel beam of light, such as a laser beam, and rays from a source. An infinite number of rays are incident on the boundary. Although for simplicity, we focus on a single light ray, and the reflection occurs at the boundary, but is usually very weak and is ignored here. Yeah. When we talk about this is some conditions we need to pay attention to. Yeah, like here are some reflection of parallel and point source rays, and you can see reflection of a parallel beam of light. Yeah, and this is a reflection of rays from a point source. Yeah, it have the angle change. Yeah, that makes sense to you? Okay. The angle between the incident ray and the normal is the angle of incident. Yeah, we talk about this. Yeah, in the like a reflection. And the angle on the transmitted side mirrored from the normal is called the angle of refraction. Yeah, which means this is the angle of incidence, and this is the angle of refraction. And the angles are the same for the ring entering medium 2 in the first figure, and the ring exiting medium 2 in the second figure. Yeah, the figure are the same for the ring entering medium 2 in the first figure, and the ring exiting medium 2 in the second figure. Yeah. Yeah, this means this angle, this angle, yeah, the ring enter into this medium, this angle equal, yeah, this angle, the ring exiting this medium too. Yeah, those two are the same, a same angle value. Yeah. Okay. In 1621, Dutch scientist Wilbur Snell proposed a mathematical statement of the law of refraction, now called Snell's law, N1 N1 multiple sin theta 1 equal N2 multiple theta 2. Yes, Snell's law for refraction between two media. Yeah, the N1, N2 is just like the index of refraction in material for material 1, for material 2. That the index of refraction determines how much a light ray is bent when crossing the boundary between two different media, a consequence of the change in the spin of light as it crosses a boundary. Yeah, this the Snell's law tell us how much a light ray is bent when crossing the boundary between two different medium. Okay, the Snell's law shows when a ray is transmitted into a material with a higher index of refraction, it bends to make a smaller angle with the null. And when a ray is transmitted into a material with a lower index of refraction, it bends make a larger angle with the normal. Yeah, you can see here, this is Snell's law. It is, sorry, it is N1 sin theta 1. equal n2 sin theta 2. Am I right? Yeah, which means n1, for example, it is air, and sin theta 1 is a fixed thing. If it's into a higher index, which means this one is become bigger, which means this one will become smaller, and then it will equal this one. Am I right? Which means a higher index of refraction will make the angle become smaller. That makes sense to you? If the index of refraction like lower, yeah, which means if it is lower, yeah, if this one is lower, which means this one will be higher, like to make sure the value, the multiple value equal this one. Does it make sense to you? Yeah, this is Snell's laws, like want to tell us. Yeah, and this is some like indices of reflection. Actually, we talk about this some in chapter like 17, and you can see the in the vacuum the index of reflection is 1, and in the air actually it is 1.0003. We usually use 1, like just the same in the vacuum, like in some problems. And yeah, this is water, some oil, gas, glass typically, and this is some like plastic. This is some zirconia and some diamond. Yeah, this is some common like index of refraction we usually use. And let's try to understand how to analyze refraction. Firstly, when you meet some problems that you to analyze refraction, firstly you draw a ring diagram. Yeah, represent the light beam with one ring, and draw a line normal. Yeah, perpendicular to the boundary. Do this at each point where the ring intersects a boundary, and show the ring behind in the correct direction. The angle is larger on the side with a smaller index of refraction. This is the qualitative application of Snell's law. And label angles of incidence and refraction. Measure all angles from the normal. Use Snell's law. Calculate the unknown angle or unknown index of refraction. Yeah, this is like the steps to analyze refraction. Yeah. Okay, let's talk about some like quick check questions. A laser beam passing from medium 1 to medium 2 is refracted as showing, which is true. You can see here the like this one. Yeah, it just lets you to like tell if the index of refraction, which one is bigger, which one is smaller. So what we need to do is just yeah, there is a refraction phenomenon, and here we want to get this. No, this is theta 1 and this is theta 2. You can see obvious the theta 2 become bigger. Am I right? Which means the index will become smaller. Am I right? So, which means n1 greater than n2. Yeah, because theta 1 smaller than theta 2. That makes sense to you? Yeah, so which means the right answer should be B. Yeah, because it bends away from the normal. Yeah, this like angle become bigger. Yeah. And let's talk about the other one. A light rain enters a glass prism as showing, which is a possible path for the rain through the prism. Yeah, we know like the index for the index of refraction for air is smaller than to the other material. So which means from the air to some like a glass prism, and the angle, yeah, should become smaller, right? So which means this is the no, yeah, this is the no, yeah, and this one, let me make it clear. Oops. Yeah, this is the no, yeah, and which means, yeah, this one and seems become, and the angle, yeah, become like bigger, which means the index fraction become like a smaller. It's not right. I'm right. Yeah. Let's talk about this one. This is yeah. And this one, yeah, this one you can see the angle becomes smaller, which means the index reflection become bigger, and this one is right. But for this one, yeah, you can see, and this one, yeah, which means this one, the angle becomes smaller, which means the infraction, the index of refraction become bigger, which this one is not right. So this one is also not right. Yeah, it's a similar thing if you analyze using the Snell's weight, and this one is also not right. The right answer should be D. Yeah, yeah, you need to like draw the norm and to see if the angle become bigger or smaller. Yeah, it should become smaller, like when you enter into this. Yeah, 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 because the index of infraction become bigger, so which means the angle should become smaller, and when you enter into this one, and the index should become, the angle should become bigger. Yeah, so this one will be the right answer. Okay, let's talk about one example, like measuring the index of refraction. Yeah, this figure shows a laser beam deflected by a 30-degree, 60-degree, 90-degree prism. What is the prism index of refraction? Yeah, here is give us this angle. Yeah. Okay, this is a laser beam, and this is refraction situation, and we will represent the laser beam with a single ring and use the Rain model of light. Yeah. Okay. Yeah, the figure shows a laser beam deflected by 30, 90, 60, 90 prism. What is the prism's index of refraction? Yeah. Okay. Okay. I think I just repeat it. Yeah. Okay. Like this figure use the steps of text box 80.1 to draw a rain diagram. Yeah. And the rain is incident perpendicular to the front face of the prism, like theta I equals 0, like that. Thus, it is transmitted through the first boundary without deflection. At the second boundary, it is especially important to draw the norm to the surface at the point of incident and to measure angles from the norm. Yeah, this is the steps we need to follow. And yeah, I think I just repeat this. Sorry. And from like yeah, this is a diagram. Yeah, we draw it, and yeah, this is the incident line, and this is the light, and this is the refracted light, and this is the norm, and this is the angle it has give us. Yeah, it is here. Yeah, this is the same angle here. Okay, and yeah, we know like this is 30-degree. Yeah, this is the 60-degree because this is 90-degree, right? So which means yeah, this is 90-degree, right? So which means this is 30-degree. Yeah, and for the incident angle is 30 degree, and the infracted angle is what? Is this is 22.6. Am I right? So this and we want to get this angle. Am I right? So yeah, this angle it has tell us it is 22.6. Right? So okay, wait for a moment. Yeah, this phi. Yeah, phi equal this one, and this one is oh, okay. Oh yeah, we want to calculate the angle to the norm. Yeah, this is the norm. So this is what we want to know, and this is 22.6, and this is what? This is 30. So this the total angle is 52.6, am I right? Because you need to add 30 degree, am I right? Yeah. So like for the solution, from the geometry of the triangle, we found that the laser angle of incidence on the hypothesis of the prism is theta 1. Yeah, here is equal 30 degree. The same as applied angle of the prism. Yeah, is here. Yeah, this one. And the ring acts the prism at the theta 2. Oh yeah, and this such that the deflection is y equals theta 2 minus equals theta 1. Yeah, this one is just like a similar, very similar with what I gave to you, and it just a letter. This is equal 5, this is theta 1, and the total is theta 2. Yeah. So like it just let the phi equals theta 2 minus theta 1 equal 22.6. Like theta 2 equal what? 5 plus theta 1. Phi equal to 22.6, and theta 1 equal what? 30. So it is 52.6. And knowing both angle and N1 equal 1 for air. So we use Snell's law to find N1. N1 equal this thing, because N1 theta 1 equal N2 theta 2, am I right? Yeah, so N1 equal 1. This we just put a theta 2 here, theta 1 here, and we can get this value 1.59. Yeah. And we can compare this one with here. Yeah, no, this here. Let me see. Yeah, here. Yeah, you can see it just kind of a plastic. Yeah. Yeah. Okay. Yeah, let's accept this question, like referring to the indices of refraction in table 80.1. We see that the prism could be made of polystyrene, like a plastic. That would make sense to you? Okay. Let's continue talk. Okay. Let's talk about this example. Like what is the index of refraction of the plastic if a rain is refracted as in the figure? Yeah, here this is air, this is air, this is plastic, and this is incident rain, and this is in refracted rain. So like we know that the index of refraction for this one is equal what? Is equal, we have the equation like this equation, Snell's law. That makes sense to you? Yeah, here. Yeah, this one. We can calculate the index of infraction using this equation. And okay, so yeah, like we know like n1 sin theta 1 equal n2 sin theta 2. So this is like a for the air, the n air is just about around 1. So like sin, yeah, theta 1 equal n2 sin theta 2. Yeah, this is theta 1. Yeah, just like a bit, just pay attention. You cannot use this angle, this angle. You need to use the angle like between the incident line with a norm line, and this for this one is just the refracted line between the reflection and the norm line. So this is your like theta 1 and this is your theta 2. Does it make sense to you? So which means theta 1 sin 45 degree equal n2 sin, this one is 35 degree, 35 degree. So which means n2 equal sin 45 degree divide sin 35 degree. So you just calculate this to get the plastic index of refraction. That makes sense to you? Okay, I will leave this to you. Okay, let's talk about one atom. Yeah, total internal refraction. Yeah, like the short name is TIR for total internal refraction. What is total internal refraction? Internal refraction occurs when a light ray is unable to refract through a boundary. Instead, 100% of the light reflects from the boundary back into the present. You can see here, this light, yeah, this light is just like it will not like refracted through this boundary. It will reflected. Yeah, this situation we call it total internal reflection, like a TIR. Okay. Yeah, like crossing a boundary into a material with a lower index of refraction causes the ray to bend away from the norm. Yeah, actually, this like a total internal refraction. It happens when a like ray it cross a bond into a material with a lower, which means this n1 small like greater than n2, like go to a lower index of refraction, cause the ray to bend away. Yeah, like to bend away from the norm. As the angle theta 1 increases, yeah, this is theta 1, this is theta 1. As the theta 1 increases, the refraction angle theta 2, you can see this is theta 2, this is theta 2. This theta 2 approaches to 90 degree. Yeah, and the fraction of light energy that is transmitted decreases. Yeah, while the fraction reflected increases. Yeah, and a critical angle theta c is reached when theta 2 equal 90 degree. Yeah, like this is the angle for theta c. Yeah, because you can see we know like n1 sin theta c equal n2 like sin theta 2, am I right? When the theta when this theta 1 equals theta c, this like theta 2 equal 90 degree, which means this one equal 1, am I right? So which means n1 sin theta c equal n2, which means sin theta c equals n2 divided n1, and then this is exactly the equation for the theta c. That makes sense to you? Yeah. So which means when the theta 1 reach to theta c, and the theta 2 will equal 90 degree, the refracted light vanishes at the critical angle, which means there will no refracted light. And if the angle equal or greater than theta c, and there is only reflected light. Yeah, there is only reflected light. Yeah, which means there is no critical angle and no total internal refraction if n2 greater than n1. If n2 greater than n1, this situation will never happen. Yeah, that makes sense to you. Okay, yeah, this is the total internal refraction. Okay, let's talk about continue to talk about total internal reflection. Actually, here is an application for the total internal reflection. And in a pair of binoculars, the lenses are much further apart than your eyes. So you can see the lens is very far. That this is your eyes. Yeah, it's very far to your eyes. Yeah, so the light rays need to be brought together. But binoculars use a pair prism. Yeah, you can see a pair prism here, forcing the light to undergo to TIRS before emerging from the eye, like a eyepiece. You can see because when the light comes through to the prism, and you don't want the light go to this direction, am I right? You just want to all the light go to your eyes. So there are two different prisms to use TIR's phenomenon to reflected all the lights to your eyes. Does it make sense to you? Okay, this is an application for TIRS. Yeah. Okay, let's try to review these equations. Let me to. Yeah. A laser beam undergoes two refractions plus total internal refraction at the interface between medium 2 and medium 3, which is 2. Yeah, we know like if there is a TIR, yeah, if the TIR happens here, which means N2, yeah, greater than N3. Sorry, the N2, yeah, greater than N3. Yeah, that's true. That makes sense to you? Okay, because you can see N2, yeah, N1 greater than N1, which means this one greater than this one. So, which means the N2 should greater than N3. Then the TIR happens. Am I right? Yeah. So the question, there are options. Just compare N1 and N3. So we need to find the relationship between N1 and N2. First, let's find the relationship between N1 and N2. You can see. Let's write down this line. So, yeah, you can see this theta 1, this theta 2. Theta 1 smaller than theta 2, which means N1 greater than N2, am I right? So which means N1 greater than N2 greater than N3, and obvious N1 greater than N3. So the right answer should be B. That makes sense to you? Okay. Yeah, the answer is B. Sorry, I just put this, it should be here. Sorry, I will modify it later. Okay, let's talk about this equation, this question. And a fish in an aquarium with flat sides looks out at a hungry cat. To the fish, the distance to the cat appears to be less than the actual distance or equal to the actual distance or more than the actual distance. Yeah, this is, let's analyze these questions. Actually, you can see this is the water. The fish is here, fish in the water. And when the fish see the items outside the fish and outside the tank, and you can see here there are some there will be refraction phenomena. Yeah, so you can see here because the water, the index of water, the index of like infraction, it for the water is greater than the rain. So this theta should smaller than this one, am I right? So yeah, this is the real cat actually. But the fish in the air, the fish in the water, so they see the cat is in this location. Yeah, but the real cat is here. then it can it will have the infraction situation phenomenal. Yeah, but the virtual cat is here. So the rain seems to come from here. This is a virtual image at a larger distance, which means, yeah, the fish will the distance to the cat appears to be more than the actual distance. That makes sense to you? Yeah. Okay, let's talk about one example. Like, where can you see the starfish? A woman lies on a paddle board floating on the still surface of a tropical lagoon, scanning the water below. A starfish rests on the sandy bottom of the lake, 3 meter below the surface. Yeah, this is 3 point. Yeah, 3 point below the surface. This is 3.0 meter. What is the diameter of the circle on the surface of water inside which the woman can see the starfish? Okay, let us analyze these questions. Yeah, if we see something that rays from the object must be reaching out our eyes, it's obvious, am I right? So we will treat the starfish as a source of light rays and consider the path of the rays to see if they make it from the water into the air. We will draw rays coming off at all angles. Only some of the rays refract into the air where they can be seen from above. That makes sense to you. You can see only this like a light. Yeah, this is the starfish, and only this light can be seen. Yeah, this one, yeah, it has a TRS, so they cannot be seen. So this distance is what we want to calculate. Yeah, we can model the starfish as a point source. Yeah, we then stretch the path of the rays from the starfish as in the figure. Rays that strike the surface at an angle greater than the critical angle. Yeah, this is a critical angle. And greater than the critical angle undergo total internal like refraction back down into the water. The diameter of the circle of light is a distance d between the 2 points at which rays strike the surface at the critical angle. Does it make sense to you? Yeah. Okay. Let's try to solve this equation. From trigonometry, like the circle diameter is d equals this one. Yeah, let's try to find why is this one. Okay, here you can see this is this one. Yeah, yeah, this is d. Am I right? Yeah, this is this d, and this angle is equal this angle. This angle we know like this is critical angle. Yeah, it is theta c, and because this one and this one is parallel. Am I right? Yeah, yeah. This one and this one is parallel. So this angle equal this angle. Does it make sense to you? Let me make it clear for you. Yeah, this is d. Am I right? This is theta c. Yeah, since this one parallel this one, and which means yeah, this is the incident line for the critical angle, which means this angle equal this one. This angle, this is theta c, and this is d. So which means yeah, this is h. Am I right? So d equal what? D equal tangent theta c multiple h. Am I right? Yeah, sorry, this is half d. Yeah, this is d. So this is half d, which means half d equal h tangent theta c. Then d equal what? 2h tangent theta c. Am I right? Does it make sense to you? Okay, this is why d equal 2h tangent theta c, where h is the depth of the water. The critical angle for a water air boundary is this one. Yeah, actually we talk about this in here. Yeah, here. Yeah, I just prove why this one equal this one. Am I right? So which means yeah, here we know the equals sin here n2 divided n1, n2 equal 1 because it is just the bigger or the smaller one. Yeah, you can see here. Let's review it. Yeah, this is the small one. This is this one, smaller one, and this is the bigger one. Does it make sense to you? Okay. So, which means we can calculate theta c based on this equation. It's around 48.8, and then we use this equation calculate d, and it is 6.9 meter. Yeah, let's assess this result. This result seems reasonable if you've ever had the experiments of looking for objects below the surface of the water. You can see objects directly below you, but you cannot see objects off to the side. Does it make sense to you? Okay. Let's talk about fiber optics. Actually, you don't need to memory those things. I just want to let you know what's the theory behind fiber optics. How a TIR can be used for fiber optics. You can see fiber optics use total internal refraction for the transmission of light through optical fabrics. Yeah, the light rays pass into the narrow diameter glass fiber, you can see here, but then strike the inside wall, you can see inside of the fiber at an angle of incidence approaching 90 degrees. This is larger than critical angle. So the light undergoes TIR and remains inside the glass. They will not go outside the glass. That makes sense to you? Okay. When the light rays reach the flat end of the fiber, and the angle of incidence is lower than the light can cross the boundary. To protect it from external damage, a glass candling surrounds the glass core, and light undergoes TIR at the candling boundary and remains within the core. Yeah, you can see here is the core. Yeah, this is the candling, and this is the protective cover. Yeah, to protect it from external damage, a glass candling surrounds the glass core. Yeah, light undergoes TIR at the candling boundary and remains within the core. And endoscopes made from the optical fibers are used for arthroscopy surgery. Yeah, arthroscopy surgery. You can see those things can be used to do some arthroscopy surgery and using fiber optics. Yeah, and this is very useful things. Yeah, in medical area. Yeah. Okay. Let's talk about another thing. Yeah, the image formation by refraction. Yeah, the part of the ruler, you can see there is a ruler in an aquarium, and the part of the ruler submerged in water in the photograph appears closer than the part above the water. You can see this part is similar, closer to us, am I right? This is further. And the rays from the submerged portion refract at the water-air boundary. Actually, here have some refraction phenomenon. And through your eye, you can see here is analyze. Yeah, this is our eye, and yeah, this is object P. Actually, this is a real object, and it will from here to the boundary, it will have the infraction phenomenon, and then our eyes will see the objects. It's just here. Am I right? So to our eyes, the rays appear to diverge not from the object, not from here, but instead from here. The ruler appears closer than it really is because of the refraction of light at the boundary. Does that make sense to you? Yeah, you can maybe you can find you can put a get a ball and put something in put the water and put something in the ball, and you will see like this atom is seem for, like closer to your eyes. Yeah, you can do this simple lab. Yeah, and the optical axis, yeah, is let's do some analysis. Yeah, this is the optical axis. Is the length through the object and perpendicular to the boundary. Yeah, this is the boundary. This is the object P, and this is the virtual image. And the distance L. Yeah, this is the distance L. Is common to both the incident and the reflected rays. Yeah, this is like incident, and this is reflected. And this is no. Yeah. So this is the distance between the optical axis and the node. Yeah, and then we can calculate this distance. Yeah, because this is just this distance, am I right? And this is the theta 1, and which means and this is theta 2, am I right? Yeah, which means this is theta 2. So which means like this distance equal, this is theta 1, this is this distance equal here, this is S, and this is S dot, and L equal S tangent theta 1, also equal S dot tangent theta 2. Does it make sense to you? Yeah. Let me try to make it clear that you to see. Yeah. Yeah, this is S, this is S dot, and this is 1, and you can put it here, which means that this one equal, and this is S multiple tangent theta 1, and also this is S dot, this S dot, yeah, S dot multiple tangent theta 2, right? And we can have this equation. From this equation, we can get this equation. S dot equal tangent theta 1 divided tangent theta 2 and multiple S. Snell's law relates the angles. Yeah, this is a Snell's law we can get. Yeah, sin theta 1 divided sin theta 2 equals n2 divided n1. And using the small angle approximation, like we can get this equation. Yeah, because if the theta 1 theta 2 is very small, and the tangent theta 1 divided tangent theta 2 approximately equal to like sin theta 1 equals sin divided sin 2, and then we can know that it equal n2 divided n1, and then we can get the image distance is what? Is x dot equal, yeah, because this one equal n2 divided n1, right? So s dot equal n2 divided n1 multiple s. That makes sense to you. This is why we can get this equation. Yeah, this is equation 18.7. And let's talk about one example. Where are your feet? And Ruben is working in a shallow, clear bin in still water just over her knees. When she looks down at her feet in the sand, she notes that they appear closer to her than usual. Normally, when she tips her head forward to look at her feet are 1.6 meters from her eyes. How far away do her feet appear when they are under 0.6 meter of water? Let's talk about the strategy for this problem. There is a refraction at the surface of the water that will lead to a difference between the image distance, the perceived distance to her feet, and the object distance, and the actual distance to her feet. Yeah, does it make sense to you? Okay. let's do some preparation. Like Rowan's feet are the object. Yeah, this is the object. And she observes with her eyes. This is her eye. In equation, 80.7, like this is S dot equal like N2 divided N1 S. I'm right. So N1 is the index of refraction of the medium the object is in. Yeah, which means it is water. Am I right? 1.33. N2 is the index of medium the observed is in the air. So the N2 equal 1. All right. So the quantities S and S dot in equation 80.7 are the distance of the object of the image. Yeah, object of the image from the from the boundary and the surface of the water. Yeah. These distance are shown in figure. Yeah, this is the S and this is the S dot. Yeah, this is the image of the image of the boundary. This is the image and this is the boundary and this is the real object. And yeah, oh sorry, this is the repeat one. We just ignore that. And let's resolve this problem. Yeah, we use equation 80.7 to find the image distance as dot here. We just talk about this is the equation 80.7 and we can here this one is 1. We talk about it. This is water and this is 1. This is air. This is water 1.33 and this is this distance to this distance is 6 meter. Yeah, this is from the question. This one, how far to appear when the 6, yeah. And so which means this is 0.6 meter. Yeah, which means this S dot equal 0.45 meter. Yeah, the total distance to the image of her feet is this one. Yeah, I just should put it here. Sorry, and this distance is this distance is 1. Yeah, because this distance is 0.6 and the total is 1.6, so this is 1. So which means this plus this one is this one, like 1.45. This is this is the total distance to the image of her feet. Yeah. And this is noticeably closer than the actual distance. That makes sense to you? Yeah. If you have ever looked down at your feet while standing in the water, you have observed this effect. Your feet really do seem too close. You can do this in your maybe you can put some water in some conditioner, in some container. Yeah, you will observe this situation phenomenal. Yeah, you can do this lab. Okay. Yeah, this is what we talk about in this class, and we talk about many focus on the rain model of the light and some reflection, like a refraction, and the image formation. Yeah. And you what image formation what you need to know is just to how to calculate angle and distance using the equations we talk about in this class. Yeah. Okay, I will do some summarize next class. Okay. So bye, and I will see you tomorrow. Okay.